Hey everybody, so this is going to be going a little bit more in depth on thermochemical equations. So thermochemical equations are basically chemical equations that we've been working with up until this point. The reason they're thermochemical is we're basically including the heat term in some way, shape, or form. So that heat term is going to be that delta H that we've been talking about, so that change in energy within the system. We've talked about two different ways that we can write out the heat term within an equation. Where did it go? Where did it go? Oh, okay. So we can include the heat term off to the side of a reaction, like this. So we can write semicolon delta H and then include the value, or we can include the heat term into the reaction and either putting it as a reactant if it's endothermic, if the energy is being absorbed, or put it as a product if it's exothermic, if the energy is being released. So as we get into more thermochemical equations, something that is going to be helpful is being aware of some of the shorthands that are commonly used. So as you can see, all of these have delta H written on them, so they're all talking about the heat term. And then we've got these little subnotes, if you want to call them, right next to them to kind of abbreviate some different ideas. So for example, delta H of VAP is the delta H of vaporization. So this process of going from a liquid to a gas. So we can talk about the energy involved with going from a liquid to a gas. Similarly, we can do the delta H of con, which stands for condensation. So going from a gas to a liquid. One weird one is delta H of fusion. Fusion is another way to say melting. So again, if we're melting, we're going from a solid to a liquid. And then delta H solid is solidification, which may be implied, but maybe not, is going from a liquid to a solid. So these are all of those different phase changes we've talked about, okay? So liquid to gas, gas to liquid, solid to liquid, liquid to solid. And one thing that you could probably infer, but may be helpful to know, is let's say you've got the delta H of fusion, okay, so the delta H of melting. So going from a solid to liquid. As we know, if we're going from a solid to a liquid, we are breaking IMF. So we're breaking IMF, the particles are getting farther apart. In order to break the IMF, that requires energy. So that means that this process would be endothermic. As you may remember, endothermic reactions all have positive delta H's because energy is going into the system, because energy is being absorbed in order to break the IMF. So let's say something has a delta H of fusion of 15 kilojoules per mole. I'm just making up a number. So it takes 15 kilojoules per mole in order to melt something. Well, that would be equal to the delta H of solidification, but just a negative value. So as you know, solidification, going from a liquid to a solid, energy is being released. Energy is being released. That means energy is leaving the system. That makes this process exothermic. And as we know, exothermic reactions are negative because energy is leaving. So notice that's why we've got a negative sign in front of here. So the delta H of fusion, if it were 10, the delta H of solidification for the same compound would be negative 10. And again, all the negative is communicating is whether or not the energy is leaving or entering the system. You can't actually have negative energy, right? So the negative is just communicating the direction in which the energy is flowing. The same thing here is true for vaporization and condensation. So vaporization and condensation are opposite reactions of one another. So vaporization would be the positive one, energy entering, and then condensation would be the negative one, the energy leaving. Some other common delta H abbreviations you might see is delta H F, and that delta HF stands for formation. Formation is another way to write out a synthesis reaction. So if you recall, synthesis reactions is basically synthesizing a compound from its elements. So here, we'll do a throwback. Let's write the synthesis reaction for carbon dioxide, okay? So we want to synthesize carbon dioxide. So we would like to create it from its elements. So I'm going to write that prettier. So if we're going to synthesize carbon dioxide from its elements, we're going to need carbon and we're going to need oxygen, right? As you recall, oxygen is diatomic, so there needs to be two of them. Carbon is a solid at room temperature and oxygen is a gas. This is all balanced and good to go. Boom. That is the formation of carbon dioxide or the synthesis of carbon dioxide. So then I could write the delta HF of carbon dioxide over here if I wanted to. One thing that's really careful, that you need to be careful of when you're working with anything that's delta HF formation, so the synthesis reaction, as you recall, these values are always kilojoules per mole. So I don't know the value of carbon dioxide off the top of my head, but since it's always per mole, you should always be making 1 mole of whatever you're forming. So for example, if we write out the kilojoules per mole of, let's do water. Okay, so we're forming water. Okay, that's an L. My handwriting's getting worse as we've been doing it anyways. So we're going to synthesize from hydrogen and oxygen. Both of these are diatomic. Okay, both of these are a gas. So if we were to go ahead and balance this, I've got 2 oxygen over here. I've only got 1 over here. So we would balance this like this. Here's the problem. If you were going to write the delta H formation of this, and it's kilojoules per mole, notice how I'm actually forming 2 moles of water. But the value, like if you Googled up delta H formation of water, it's always only per 1 mole of water. So in writing out this equation, we kind of cheat a little bit. We really only do this with thermochemical equations. If I only want to form 1 mole of water, basically I need to divide by 2, right? If I divide by 2 over here, then I get 1. So that means I have to divide by 2 over here, which means I need to divide by 2 over here. I only have 1 to begin with, so what's 1 divided by 2? Half. So I'm going to go through here and make this look better. I'm going to change my color. The better way to write this in terms of a thermochemical equation is to put a half in front of the O2. Now, can you have half of an O2? No, you can't. Oxygen's diatomic. That doesn't exist. But in order to make this thermochemical equation correct, and we only want 1 mole of water, we would put the half O2 in order to make it work. Again, this isn't good in terms of like what actually happens in nature, but when we're expressing this value to per 1 mole, that's why we do the half. The other option you have is if you wanted to write this out correctly, you would need to double this value. Because if this is only talking about 1 mole of water, you would need to double it to reflect the 2 moles of water over here. So just something to keep in mind as you write these out. All right, here's a couple more. We've got the delta H of combustion. So we say comb for combustion. So combusting any materials, so the delta H would be the value for that. If you recall, combustion reactions are always exothermic, so these values are always going to be negative. Remember, delta H is negative, energy is leaving. And then the other one is delta H sol. That is for dissolving. So the sol stands for solution. It's basically writing a dissolving equation. So these are some shorthands that you should be familiar with. So I could say like the delta H com of ethanol is this, and you should know I'm talking about the heat involved in combusting ethanol. I could also write delta HF of ethanol. So that would be the energy involved in forming ethanol from its elements. So let's do some practice with this. So I've got the, all right, so write the thermochemical equation for the vaporization of water. And I gave you the delta H VAP of water, 40.7 kilojoules per mole. All right, so let's go ahead and dive in here. So the first thing you need to know is what is vaporization. Okay, so vaporization is going from a liquid to a gas. So I'm going to just write the equation first. So that's going to be water, that's a liquid, turning into water, that's a gas. That's all you do. So that is the chemical equation for vaporization, just liquid to gas, done. Now I'm going to look at the heat term here. So this value is positive. Okay, so it's not negative, therefore it's positive. I also know that vaporization is an endothermic process that energy needs to come in. So if I'm writing a thermochemical equation, you can write it one of 2 ways. I'm going to write the heat term in the reaction for this one. So I'm going to write 40.7 kilojoules. You can write kilojoules per mole. That would actually probably be better. But do you notice how all of these just have 1 mole of water? So if you want to save yourself the time and the energy, you could just write kilojoules. And then notice I wrote it as a reactant. Because delta H is positive, energy is going into the system. This is endothermic. The energy is going to be a reactant in this case. So, done. That's it. That's all you got to do. You could have written the semicolon notation. Both are fine. Both are valid. Honestly, if I ask for the thermochemical equation, I'll either be specific, and if I'm not, you can do either one. Okay, let's try the next one. Write the thermochemical equation for the vaporization of methanol. So, it'd help if I had methanol on here. There we go. Now we have it. So this is methanol. It's an alcohol. So if we're vaporizing, we're going from liquid to gas. So there's liquid methanol to gaseous methanol. All right. Notice vaporization. This is a positive value. Again, because this is going to be endothermic, all vaporizations should be endothermic. So 35.2 kilojoules, writing it as a product, it's on that side. Awesome. Now we've got, write the thermochemical equation for the fusion of methanol. Remember, fusion is melting, and melting is going from a solid to a liquid. So I'm going to write methanol again. All right. And I'm going from solid methanol to liquid methanol. Again, this is another positive delta H value because it requires energy to break the IMF. So I'm going to write the 3.17 kilojoules over here. So these are examples of how you'd write thermochemical equations. Let's dive a little bit deeper though with some of these questions down here. All right. Why is the delta H for vaporization for water greater than methanol? So if you notice, water was 40.7 and methanol was 35.2. So we know water is greater, but why? Well, they're both vaporizing, so they're both going from liquid to gas. Water requires more energy, and must be because water has a higher IMF. If it takes more energy to turn water into a gas than methanol, you must be requiring more energy to break more IMF bonds. Because remember, you're changing IMF when you're doing phase changes. Why is the delta H of vaporization for methanol greater than the delta H of fusion? So remember, vaporization is going from liquid to gas, and fusion is going from solid to liquid. Well, which one are you breaking more IMF? Liquid to gas or solid to liquid? Liquid to gas. Again, you're breaking more IMF when you're going from a liquid to a gas because you're going from a fair amount of IMF to literally no IMF. So you're breaking so much more. So that takes so much more energy. Why do you think delta H of, what do you think the delta H of condensation is for water? Remember, con stands for condensation. Well, condensation is going from a gas to a liquid. Well, if you look up here, I've got the delta H of vaporization for water, and that's going from a liquid to a gas. So vaporization and condensation are opposite of each other. So it must be the delta H con for water must literally just be the opposite of vaporization. So negative 40.7 kilojoules per mole. Meaning, it's not negative because it takes negative energy. In this case, it's exothermic, so energy would be leaving the system, which is why it's negative. All right, so with thermochemical equations, just like with regular chemical equations, we can do stoichiometry with them. To save some time, I already wrote the thermochemical equation for the above reaction because we're going to be needing to use it in order to do this problem. So I wrote the complete combustion of methanol below. And notice I did one of those weird half things again. Remember, these values are kilojoules per mole. And since it's of methanol, I needed 1 mole of methanol. In order to get only 1 mole of methanol, I had to do one of these weird 3/2 things. So you can do 3/2, 5/2, whatever, in order to make it work. So I only had one of these. So I could keep that 726 value. So to go ahead and do my problem here, I've got 20 grams of oxygen and I want to know how much heat is released. So I will take my 20 grams of oxygen, put it over 1. I can convert grams of oxygen to moles of oxygen like I've always done. And then what you're going to do here is you're going to go from moles of oxygen to basically moles of kilojoules. So if you look at this, my ratio is 3/2 to 726. So 3/2 oxygen and 726 kilojoules. So that's my ratio between the two. And when you calculate your answer, you get this. So really the only new thing to keep in mind when you're doing stoichiometry with these thermochemical equations is the ratio. And you're going to do the ratio just like we've always done. Essentially, you're going to take like whatever coefficients you have in front of here, and basically the amount of energy is its own coefficient. So when 3/2 of oxygen react, 726 kilojoules are formed. So the ratio will